Good morning, everyone. In the last class, we have seen the IGBT based three-phase inverter. Now, today I would like to explain the multi-level inverters, the three-level inverter. So this is a three-level bridge. You can see in the power electronics devices. You can identify this one. Simscapes, Sim Power Systems, specialized technology, fundamental blocks, power electronics. This is the three-level bridge. You can get it. So similarly, you'll get a PWM generator, three-level. This is PWM three-level. Three-level is obtained here. So in addition to plus and minus DC side, you have neutral point, so that you can increase the level plus VDC by 2 and VDC plus VDC by 2, 0. Similarly, negative side. Here 200 volts positive, negative side minus 200. DC side. AC side, you'll get a three-phase supply. So sinusoidal pulse width modulation. This is phase, first phase, frequency 2 pi into 50 radian per second. 2 pi by 3, phase 2 pi by 3, frequency 2 pi into 50 radian per second. Third phase 2 pi into 50 radian per second, phase 4 pi by 3. And here you have AC side resistive load, three-phase resistive load, 100 ohms. And all these are the measurements. VABC and IABC measurements. And RMS value, THD, etc. Okay, so you can get sim output. Now 3-phase resistive load is grounded, and this is a firing PWM control. You can use discrete type 15 to e power minus 6. Now you can run this simulation. This is the V output. This is open loop control without any filter. And format structure with time, scope data, apply, OK. And here also this is the current. Structure with time, apply and OK. And the preferences 50 Hz. Remaining you can keep as it is. And FFT analysis. So you can look at this scope 1, scope these two. CMOT 1. And second you can run this. Hz, you can change this one. Tools FFT. Start time you can use 0.4. Number of cycles 10. Frequency 50 Hz. And maximum frequency 1000. 35.15. This is the FFT window. Input 3. All are same, 33.9 around the 35.14. Small difference is there in phase 3 and the remaining two phases. 35.14. Current is also having the same THD. Phase B. Last one, phase input 3. Okay, for the third phase, some problem is there. So let us solve it. Simot 1. So there is some problem in phase 3. Again, you can run this. Structure with time, apply and OK. Now let us look at this. 50 Hz. Tools FFT analysis. And this is scope 4. So this is the 3-level bridge IGBT based. IGBT is a switch, but here it is GTO is used instead of IGBT. Previously we have used IGBTs. Now it is GTO. Gate turn off thyristor. SIM 2 is connected. Mostly we'll prefer IGBT or GTO, the STATCOM. Those two are turn-off devices, therefore we'll use the turn-off devices as a switches. Now SIM 2 50 Hz, apply, and FFT analysis. SIM 2 This RMS value is very low. I don't know why it is happening. We'll see. Okay, it is there. It is 50 Hz. You are not getting it. Okay. We have to diagnose it. What is this problem? We'll see that. RMS value 140, around that. This is 50 Hz. Active power. Let us look at active power. 0 and 0. Voltage and currents. Let us apply. Okay, now we will see the response. Okay, it is okay. Now let us understand sim out to preferences.
Power system harmonic analysis. అదేనా Bibin Singh, sir.
Sim out 3, we got this one result. So like that we need to diagnose our problem. This is 3-phase parallel RLC load. Instead of RLC branch, we have used the load. Anyhow, THD content is very high, 33.97. Without filter, it is like that. Now let us introduce reactive power also. Inductive reactive power. Voltage waveforms, current waveforms. Let us go to harmonic analysis. Display 25.36. Second signal 24.14. Third signal 24.13. Of CMOT 1. This is the current. CMO output 35.72, 33.97, second signal. Third signal 33.97. These are the signals for RL load. Now let us use only reactive load 0. Apply and let us simulate. This is the voltage waveform, current waveform. Now let us look at the FFT analysis, 50 Hz, FFT analysis. CMO output 35.72, 33.97, and 33.97. CMO output 1.01, current. This is the current signal. Phase A, phase B 1.01, phase C 1.03. For reactive load, the harmonics were absent in the current waveform. Of course, it is present in the voltage waveform. Okay. Now let us go to capacitive load. Now run the simulation. Now let us look at the waveforms, voltage waveform, current waveform. Now let us see the effect analysis. This is 50 Hz. Apply and tools, go to effect analysis. CMO output 1, very high, and THD is not acceptable. The current waveform is like this. In phase 3, it is like that. CMO 1, voltage harmonics 34.51. CMO output 232.76. For 3, it is 32.76. So from which you can understand very easily that the STATCOM may be more suitable for inductive loads. It also supplies the capacitive load, of course. But THD content is very high due to switching. and this is inductive and capacitive load. Let us reduce one of them, 5. Voltage waveform, and this is the current waveform. Now let us go to FFT 50. Sim output 1, okay, let us look at 35, so 33, and third one 33. Sim output 1, very high, 1, 2, 3000, 3400, 3300. Not acceptable, okay. So it may be suitable for inductive loads. Anyhow, we need inductive compensation most of the times. So it is better suited for that. And now let us see, instead of battery, we'll go for charger capacitor, RLC, RLC series branch, GTO 1. This is RLC 1. I will save it as GTO 10. Control off. Now let us use RC network to avoid error. I'm using resistance also, small resistance. Here you can use 100 microfarads. Initial charge, set initial charge of 200. Branch voltage and current apply. Now I'll remove this one. Now run this. Now let us look at the voltage waveforms. This charging capacitance is not sufficient to generate the load, so you can use 200. Let us use this to load. 1. Now we got these waveforms. Let us look at the harmonic analysis. 50 F50 analysis 16.778, the current waveform. 21 31. You can use 40 cycles. 11.02%, 13.86, 10.58. Coming to voltage waveforms, 40.18, 38.2, 38.24. Let us connect this one voltage source, DC voltage source, and simulate. Anyhow, this is very important. Voltage source converter, multi-level converter, can be used as a STATCOM, SSC, UPFC, etc., IPFC. So once you understand this one, STATCOM, very well, you are able to understand other devices. Let us look at the F50 analysis. 50 tools, F50 analysis, display 34, sim output 1, 32, 33, sim output 1, current waveform 8.3, 8.56, 1.45. These are the harmonic analysis of current waveform. Like that, you can design based on current rating of your capacitance. Voltage, applied voltage is equal to IC into XC. From XC is equal to 1 by omega C, from which you can calculate the capacitance. A small resistance is used in series with the capacitance. So once again, you can remove this one. And you can also remove resistance. We'll see. You got voltage waveform and current waveform. Go for the 50. 13.87, 10.58, second wave, third wave, 11.02. This is the current wave. This is the voltage wave, 40.18, second one, 38.22, 38.25. So anyhow, harmonics are present. Voltage harmonics always present. Maybe sometimes for reactive load, current harmonics may be eliminated. So therefore, we need to go for a filter. With filter, so this is a filter design for this circuit. Inductance 4 into e power minus 3. Capacitance 4.15 into e power minus 5. Let us run this. Now we need to get sim output. Voltage as well as current. Load resistance is 1 ohm. Now you can run this with filter. Pure sine wave. You can use to apply history. You can use one lap. Save data. Structure with time. Apply. OK. Similarly, current wave. Is to history. Save data. Structure with time. Apply. OK. Once again, run this. FFT analysis 50 Hz. Apply tools FFT analysis. What is this scope? Sim output 1. Scope V with filter, I with filter. Sim out. Point 2, 10 cycles, 50 Hz, 1000. Okay, display 1.21. Second phase 1.24, 1.14. These are the current waves. Sim output 1, 1.21, 1.24, 1.24. This is about filter, FFT analysis with filter. Okay, today I'll stop here and I'll take 30 minutes.